Okay, we then ask what should happen to the system if we suspend the mass from 2 rubber bands. And here we have the 2 rubber bands. Here's the 50-gram mass. And we can see that the oscillation increases in frequency. I'm actually going to count this here. Okay. I just got 14.5 counts. Okay, let's see if that holds up. Okay, so if we've got 2 rubber bands, what changes and by what factor in our analysis? Well, what changes, and you should think this through, make sure you understand, but the thing that most directly changes is the value of K. And you can experience this if you take a bungee cord or any kind of a chain. If I want to extend this, let's say this far, okay, and I grab a pretty good length of the chain, and then I grab a shorter piece of the chain and try to extend it the same amount, it takes much more force. So that K definitely increases when you shorten the amount of chain you have. Why is that? So by factor, well, K changes. Let's say that this represents the chain and with 4 rubber bands, and here's the chain with 2. And we assume that the rubber band masses are negligible and that the rubber bands are identical. They aren't identical, but their masses are pretty much negligible within the limits of what we can count. And we assume that they're linear. They're close to linear, but not quite. But again, within the limits of what we can measure by simple eyeball count. That doesn't make a whole lot of difference that we can distinguish. Okay, so if we have this versus this, why should K be greater here than it is here? We've got more rubber bands, so why does fewer rubber bands give us a greater value of K? You should think about this. Now, having posed that question, I didn't want to write an additional comment in here. I'm going to pause the video and write in some additional comments, and we'll talk about it. Okay, I've written in an analysis here. Each rubber band has to support the same weight. Okay, you have equal masses here. Gravity exerts equal forces on these equal masses. And if I'm holding the rubber band chain here, I've still got to support the whole weight. If I support it here, I've still got to support the whole weight, meaning that this rubber band is supporting the whole weight, as is this one, as is this one, as is this one. Where I grab the rubber bands makes no difference in how much force I've got to exert to hold it up. So every rubber band holds the same, or exerts the same force. And same here, every rubber band exerts the same force, and since we have the same mass here as we have here, the force is the same here for each of these rubber bands as it is for each of these rubber bands. So each rubber band in both chains supports the entire weight of the mass. So each stretches to the same length because the rubber band tension depends on how much force it's got to exert. Okay? That means that we have half as many rubber bands. Since we have half as many rubber bands, we have half the stretch, so that this system will only stretch out half as much as this one, because if each rubber band stretches out, let's say this far, then we've only got 2 rubber bands, so we're only going to get twice that stretch here, whereas if we got 4 rubber bands, we're going to get 4 times this stretch, or something like this. So half as many rubber bands gives us half the stretch, which gives us double the force per unit of stretch, and that's what the value of K is. That implies then that K will be twice as great. Now, what does that do to the motion of the system? Instead of looking at this, you need to think through that. Well, what it does is gives us, well, omega is the square root of K over M. If K doubles, that means omega is going to be square root of 2 times as great. So that if with the original omega, we'll call that omega 1, is just trying to decide how to write the 2 pi radians over 1 second, which would correspond to the 10 counts in 10 seconds. Then omega 2 should be square root of 2 times 2 pi radians over 1 second. You can think about why this is so. The count should be square root of 2 times as great. It wasn't really necessary to write these relationships. Omega is directly proportional to your count. So if omega is square root of 2 times as great, your count should be square root of 2 times as great. Square root of 2 times 10 counts is then 14 counts. And the counts are in 10 seconds. So 10 counts per 10 seconds should give us 14 counts per 10 seconds. And that's exactly what we counted earlier. So the counts that I made on screen before and in this case give us the same thing. The other implication is, and I don't have room to write this out, but you should understand that if I remove the where'd my, okay, looks like I dropped it. Okay, if I have the 100 grams here and remove it, then it goes to about here. And you see I have a mark here and a mark here. These marks correspond very closely with the reality. And this distance should be half the distance measured before. Before we measured 17 centimeters. Half of 17 centimeters would be 8.5 centimeters. And when we measure this, we actually get about 8.3 centimeters. If I can find my chalk, that's worth writing down. Okay, so let's just kind of isolate this. This is 8.3 centimeters here. We compare that with the 17 centimeters we got before. We see it's almost exactly half as much, showing that the 2 rubber band system does appear to have a value of K that's twice as great. It gives us half the stretch, which is going to give us double the value of K.